Most developers are buying the wrong hardware for local AI. They look at raw flops, which measures compute speed, and assume a high-end consumer card will run large models smoothly. The reality is that 90% of local model failures aren't software bugs or bad code. They are memory bandwidth bottlenecks where the GPU starves waiting for data. This video explains why your current setup chokes on inference, how this differs from training constraints found in massive clusters, and which specific architectural features actually determine if a local deployment works at scale. When you buy an RTX 4090 because it boasts the highest theoretical compute numbers, you are betting that raw math power is all that matters for running large language models locally. You expect to chat with complex agents or generate text without stuttering. Instead, your model loads slowly and then generates tokens at a frustratingly low speed. The problem is not that your code has bugs or that the software is poorly optimized. The issue lies in how data moves through the system architecture itself. To understand this failure mode, we must distinguish between compute power and memory bandwidth. In AI inference, the GPU core performs calculations on model weights to predict the next token. However, those weights are massive files stored in video RAM. If the pipe moving that data from storage to the processor is too narrow, the powerful cores sit idle, waiting for input. This is known as a memory wall or bandwidth bottleneck. Consumer GPUs often use GDDR6 memory, which offers decent speed but lacks the throughput required by modern large models during continuous generation tasks. Consider an analogy of a high-performance engine in a car with a tiny fuel line. You have built-in horsepower that could theoretically drive at incredible speeds, yet you cannot reach them because the fuel supply is restricted. In this scenario, adding more compute power does not help if the data pipeline remains constricted. The GPU becomes starved for information, leading to poor latency despite high theoretical flops numbers. This explains why a card with lower raw specs but higher memory bandwidth can often outperform a faster-looking consumer chip in real-world inference scenarios. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This limitation is particularly acute as models evolve from simple chatbots into agents requiring tool use and long-term context. Research into system architecture for AI assistants identifies memory management as the primary failure point for consumer hardware during these complex tasks. As models grow larger, they demand more data throughput simultaneously. Without sufficient bandwidth to feed the cores, the inference process stalls repeatedly. This is not a software fixable issue. It requires a fundamental shift in how we select and architect our local deployment environments. The distinction becomes even clearer when comparing consumer silicon against server-class hardware used for reliable production systems. In large-scale machine learning clusters, engineers analyze hundreds of millions of GPU hours to understand failure rates. Studies analyzing over 150 million A100 GPU hours across two state-of-the-art ML environments show that as scale increases, hardware faults become inevitable rather than exceptional. Consumer-grade cards lack the redundancy and error correction mechanisms found in data center GPUs like the A100 or TPU architectures. These enterprise chips include ECC memory to detect and fix bit flips automatically, ensuring stability under continuous heavy loads where a consumer card might crash or produce silent errors after hours of operation. For engineers designing systems that must work reliably on-premise or at the edge, this distinction dictates career-relevant judgment. You cannot treat local inference as merely a smaller version of cloud training. The constraints are inverted. Training requires massive parallelism to update weights across millions of parameters over days. Inference requires high throughput and low latency to serve individual requests in real time. A hardware choice that excels at one often fails miserably at the other if it ignores memory architecture. This brings us to the specific architectural features that enable reliable local deployment. The solution lies not just in having more VRAM capacity, but in using high-bandwidth memory technologies like HBM. These architectures stack memory vertically around the processor chip, creating a much wider data highway than traditional flat GDDR designs. This allows the GPU core to access model weights at speeds necessary for smooth generation without stalling. When selecting hardware today, You must prioritize this bandwidth metric over raw compute numbers or total VRAM size alone if your goal is consistent performance on large models. The broader industry context reinforces why this shift in focus is critical now. Scaling laws are hitting a wall where energy consumption and data availability constrain further growth through brute force methods alone. The trajectory of AI scaling forces us toward distributed edge learning, but only if the hardware can handle efficient memory access without overheating or failing under load. We cannot solve future engineering challenges with past assumptions about what makes a chip fast enough for local tasks. Understanding these mechanics changes how you approach troubleshooting and system design. Instead of debugging Python scripts to fix slow generation speeds, you evaluate your system architecture. You ask if the data pipe is wide enough for the workload. This shift in mindset from code-centric debugging to hardware-aware engineering judgment is essential for anyone building AI applications that need to run locally without constant crashes or unacceptable delays. The primary bottleneck for local AI assistance remains a matter of system architecture and memory management rather than software logic alone. As we move forward, developers must prioritize bandwidth efficiency over raw flops when planning their stacks. This ensures that the hardware you invest in actually delivers on its promise of running complex models reliably at your traffic scale. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.